Well, this is a demo presentation for how you might do your final presentation for the Bivariate analysis. Hopefully this will be useful for you. If you'll recall, we started out by gathering unemployment rates for state by state for 2015 and 2016. And we're generally interested in whether or not there's evidence that unemployment rates decreased from 2015 to 2016. Obviously, if they decreased, that would be great news for us. Our challenge is that in order to do this type of analysis, we need to understand whether the data are related or unrelated. If they are unrelated to each other, there's no pattern of relationship between them. We could use just a simple hypothesis test of means to evaluate our question. If they are related, then we should probably use a technique, maybe a regression technique, that controls for the relationship first so that we can really test whether, on a pair-by-pair basis, what has happened. So the first thing we have to figure out is whether they're related. So if they're related, if they're not related, there'd be no relationship in a scatter plot, and so it would just look like a big blob. It would be tough for you to defend the idea of drawing a line that would be anything other than just a straight line, flat line through it. Also, if you were to calculate a correlation between your two data sets, it would likely be near zero. If there is a relationship, then you should start to see patterns in your data where it becomes real easy to figure out that it makes more sense to draw a line this way than say this way to explain the data. The pattern I have up here is for a positive relationship. The pattern I have here is for a negative relationship. Positive because I can draw a line with a positive slope. It's increasing from left to right. Negative because it's a negative slope. It decreases from left to right. But either way, if there was a relationship, you ought to be able to draw some sort of a sloped line. If you were to calculate the correlation, it would be closer to either plus or minus 1 or 100%. Be closer to 100% if it's a positive relationship, closer to minus 100% if it's a negative relationship. So here's our actual data, and it looks to me like there is a pretty strong relationship, and it looks to be positive. So let's see what our statistics say. Let's see, we calculated correlation here, and sure enough, it is positive value, and it's close to 1. So that supports that it's a positive relationship. So we would generally say that it is a positive relationship. Now, we also calculated some other statistics. We calculated the means and the standard deviations. You can see that they're not that far apart, either one of those. And so while the mean decreased from 2015 to 2016, it's not clear that we can prove that there was a decrease, but it's hopeful for us. So next steps, we see evidence of a strong positive relationship between two data sets. This suggests that the simple hypothesis test of the difference between the means is probably not appropriate. It might be misleading. It might not, but it could be misleading. And so what we probably should do is plan to do something that controls for the relationship. We're going to do a simple linear regression. I did go ahead afterwards and conduct the hypothesis test of the difference between the two means so that we can compare the two results. They may confirm each other, they may not, but that way you'll kind of understand the difference. So doing the linear regression, first thing that you need to understand about linear regressions is that effectively what it does is asks you to specify a formula. Well, you specify the formula by providing it with data. We'll walk through those steps in a separate video. And what it's trying to do is to create a linear relationship between your two data sets, so the 2016 and the 2015. And to do that, it solves for an intercept value and a slope value. So the slope value we'll look at first. That's beta. And so that corresponds to when we were talking about the scatter plots, what the slope of the line that you try to fit through it is. The intercept is the thing that we're more interested in for our test, it would estimate the change between 2015 and 2016 after you control for this slope relationship. And so that's the one that we really care about here. And then there's an error term when it does this estimate, because what it's recognizing is that individual data points may not fall exactly on this line, and so it's allowing for the fact that they could deviate from the line. Using this formula, we can restate sort of our hypotheses in terms of the beta 0 and beta 1. So our alternative hypothesis is there is a positive relationship between the 2015 and 2016 unemployment rates, positive slope, and so we would expect that we have a beta 1 that is greater than 0. Our second alternative hypothesis is after controlling for the relationship, the slope, the change in unemployment rate is less than 0. So beta 0 is less than 0, implying that unemployment fell from 2015 to 2016. So the way you would think about this is, imagine that I take some unemployment rate for a particular state in 2015, let's say it's 4%, and I calculate a beta for, I have a beta for that, so let's just say it's 1. So now I'm saying that the 2016 value for that state should be the 2015 value times 1, so 4% times 1 is 4%, plus whatever this beta 0 is. And so 2016 should be 2015 adjusted for whatever beta is. And so if beta is negative, that would mean that 2016 is lower. If beta was positive, beta 0, that would mean that 2016 was higher. We're clearly hoping that beta 0 is less than 0. Just restating these as null hypotheses so that we know how to set up and evaluate our tests. Our null would be there is no linear relationship, and therefore beta 0 is equal to, or beta 1 is equal to 0. Our null hypothesis for the intercept would be that after you controlled for any relationship, assuming there is one, again, these two are evaluated independently, so you could say there is one, but if there is one, then we would expect that the unemployment rate is greater than or equal to 0. That's the null, because what we really want is to say it's less than. And so we would expect to see a beta 0 of either 0 or positive. And both of those would be our null. So what the regression is going to do is estimate that line. So using the equation that we had on the last slide, it's going to estimate the line and then evaluate whether or not there is enough evidence to suggest that the parameters for that line are different from 0. So we ran our regression. Again, there's a different demo of how to actually do the regression in Excel. But let's focus, now that we have the results, let's interpret them. First thing we would look at is the R-square. We got an R-square of 0.76. The most your R-square can be is 1 or 100%. Basically, this describes how much of the variance in the 2016 data can be explained by this line that we've estimated. And so it explains away 76% of our variance, which is great. That basically means that it's doing a good job. Next thing we want to look at is we want to look at our beta 1 to see if there's a relationship. Beta 1 in this case is this 2015 value. And the first thing we look at, we don't look at the coefficient first, we look at the p-value first. And if there is a p-value, if there's a relationship, then the p-value is less than 5%. Our p-value is, in scientific notation, is practically 0. So we would reject our null hypothesis because our p-value is so small, and therefore we would conclude that there is a relationship. Now that we conclude that there is a relationship, we would go look at the coefficient. It's positive, and so that suggests that it's a positive relationship. If this p-value was not significant, we would have concluded there's no relationship. Okay, and it wouldn't matter what this coefficient was; we would just ignore it because there's not statistical evidence that it's different from 0. We could also look at our confidence bands for this, lower and upper 95th percentile bands. We're, of course, interested more in the lower one in this case. We can see that that's at 0.68. And so basically what that's saying is I would have needed to see a coefficient. Sorry, I'm saying that wrong. Well, never mind that. Bottom line there, those coefficients are wrong. We'll just ignore that. Anyway, so now that we know there's a relationship, now we're going to try and test our real hypothesis. Did the unemployment rates fall? So again, we'll look at the intercept this time. That's our beta 0. And if the p-value is less than 5%, we're going to reject the null hypothesis that the intercept is 0. It is less than 5%. So that's awesome in the respect that it basically says we know the intercept isn't equal to 0. However, when we go look at what the value of the intercept is, we were hoping it would be negative, saying that 2016 was lower than 2015. We're actually getting a positive, about 0.74. And so the sign of the coefficient on the intercept being positive means that it is suggesting that unemployment rates actually rose by about 0.74% from 2015 to 2016 after you control for sort of the state-by-state variations. So it's a little bit surprising result compared to what we thought we were going to get, but it is statistically significant. It's just not in the direction we thought. So here's what that regression analysis, all the math, here's what it looks like visually. Again, that's our original data. Here's the line that it fit. You can see the same parameters out there. And I extended this line a little bit just drew over it so that you could see that basically this intercept is, if we extended the line all the way out to the horizontal axis, where would it cross that axis? And you can see that's at about 0.74, 0.75. So that's the intercept piece. And the slope is just a question of for every 1 unit that unemployment rises or is higher in 2015, how many units is unemployment higher in 2016? And so this is just, again, a visual representation. The R-square of 76%, again, really speaks to the fact that we explain a lot of the variability in our 2016 data. Remember, the variability in the 2016 data is how much variability there is on this vertical axis. We explain a lot of it by this line. If it weren't for that, we'd be drawing a straight line through this, and we'd have a lot more space between the dots and the straight line, the flat line, than we do this sloped line. So we're by creating this slope, we're explaining away about 76% of that variability. So our hypothesis evaluation for the regression, we do conclude there's a linear relationship. Once we control for this relationship, we conclude that unemployment actually increased by about 0.75% from 2015 to 2016 after we control for state-by-state variations. The slope, this 0.816, effectively think of that as how tilted this relationship is. And what it's really saying is if you had a relatively low unemployment rate in 2015, all other things being equal, it's likely to have had a greater effect. I guess hard to explain this exactly, but that 0.74% average that things went up, it's actually going to go up by a little more than 0.74% if you were in the low unemployment rate range as a state. And the tilt's going to be the other way. You're going to go up by a little less than 0.74% if you're at the higher end. And so, I guess some good news for those of us that are in the higher unemployment range, that it maybe isn't going to go up by the full 0.74%, something less than that, but it still went up on average. So now we're going to do a hypothesis test of difference in the means, just so that we can compare the two results. Here our alternative hypothesis is that the 2016 unemployment rates are less than the 2015. I know we found evidence the other way, but we want to do the test the same way just to see if it gives us additional evidence. And so our null is that the unemployment rates for 2016 are greater than 2015. If we reject HO, then we demonstrate the unemployment rates have fallen. If we fail to reject, then we say there's not enough evidence to say they've fallen, and so they may have either remained the same or risen. So mathematically, we'll set up our hypothesis as that the population mean for unemployment rate for 2016 is less than the population mean for 2015. You'll see I took away the little state indicator on that. That's because when you do these kinds of tests, you're not looking at it on a state-by-state basis. You're just looking at the mean overall. So you're not controlling for those state-by-state differences like you do with the regression. So our alternative hypothesis then would be that the population mean is less than, right? Because that's what we want to look for. And our null is that the population mean for 2016 is greater than or equal to. It's a one-tailed test. I'll show you that. It's a one-tailed test because we're only evaluating in one direction. So if we are wrong, we're only going to be wrong in this particular direction. It is a left-tailed test because our null hypothesis is basically that the values are going to be positive, right? They're going to either be 0 or positive, this difference. And so we would reject by having a value that's so far to the left and so negative that we would say there's no way that this sample came from populations that had a mean of 0 or a mean that's positive. So we run through our calculation steps. Again, kind of explained how to do this in a prior video. But basically, the research question, are the 2016 unemployment rates lower than 2015? We've set up our hypotheses. We've already explained we're going to use a 5% significance level. We calculate our t-critical values using these different formulas. And our rule is that if not our critical values, our statistical values. Our rule is if the t-statistic is less than the t-critical, which we'll pull from our tables, or if the p-value of our t-statistic is less than the p-critical, which is 5%, then we'll reject HO, otherwise we will fail to reject. So here's our results. We calculated the t-value is minus 0.78176. The critical is minus 1.66. So the t-stat is not to the left, and therefore we could not reject. Same thing, our p-value is 22%. It's not to the left of 5%, so we can't reject, so we will fail to reject the null. Failing to reject the null means that we did not find evidence that 2016 unemployment rates are less than 2015 unemployment rates. Instead, we can't reject the hypothesis that they're either equal or that the 2016 is higher. And of course, this is consistent with what we thought before, or what we found from the regression. So both of those suggest that our original hypothesis is probably wrong. Overall, we found that there was a positive relationship, so we do need to control for state-by-state variations. We rejected the hypothesis of no change for 2015 or 16 with our regression analysis, but we actually found there was a positive change, and our hypothesis test of difference between means failed to reject the possibility that the sample came from a population where either the means were equal to 0 or that the 2016 mean was actually higher than the 2015 mean. And so again, we get somewhat similar results. Based on all of this, I would say we have pretty compelling evidence that unemployment rates likely rose from 2015 to 2016 rather than falling. And that concludes this.